Okay, so we're going to continue the discussion on topic 3, which is equilibrium of a particle. And the last thing we did was we went over example 3 right here. And we're actually going to move on from 2D force systems now and talk about 3D force systems. So very similarly to 2D force systems, where we're summing forces in the x direction and the y direction, with 3D force systems, we get to add an extra equation for translation, and we're summing all of the forces in the z direction, and we get to set that equal to 0 now. So I'm going to jump right into an example, since we've already talked about this actually for vector analysis. Again, moving to force systems is very similar. So example 4 here, we have a 90-pound load that is acting purely in the negative z direction. And we have a cable and hook system here that is supporting this 90-pound load. We're given some information about what's happening in the problem. So we're given the stiffness. Of course, we're given the mass, or I'm sorry, the weight in this case, because this is in pounds. And what we want to know is, let's see, determine the force in the cables and the stretch of the spring for equilibrium. And they're giving us this information here. Cable AD lies in the XY plane and cable AC in the XZ plane, because sometimes it's difficult to discern from a picture like this, from a 2D picture, which direction those forces are acting. So the problem will often tell us in order to help us figure out what's going on. So I'm going to start by actually coming over here. You can either draw your FBD directly on the image, or we can draw it, I can actually go like this, on the side here. I'm just going to draw it off to the side. Here we have the center, and we have that 90-pound weight that's being pulled. And then we have the spring force, which is directly along the y-axis here. So I'm just going to call this F in the B direction. And then we have this force FC, which is directly in the XZ plane. So it's kind of difficult to draw it like that. It's going in this direction, but it's really only in the XZ plane. So what I'm going to do, I'm going to call this FC, and then in parentheses, I'm just going to put XZ so that I know that's actually just in that XZ plane. And then my last force is AD. So I'm going to draw that force in the direction that's shown, FD, and I'm going to write here XY because the problem had told us that's in the XY direction. And then just for reference, I'm going to draw here the Y direction, negative Y and positive Y. And of course the negative Z, positive Z are already shown, and X as well. Okay, now that we've drawn our FBD, this is our free body diagram, we can go ahead and start summing our forces, right? So now we have our 3 equations of equilibrium that we get to use. So I'm going to start here with the sum of forces in the x direction and set them equal to 0. So which forces do I have in the x direction? Well, I know that FC acts in the XZ. So I have to have a component of that in the x direction. So my FC, I know here just from the picture, we're dealing with a 3, 4, 5 triangle. Just highlighted that, right? So the x direction there is going to be the direction which acts in line with the x-axis. So I'm going to actually get rid of the highlight so I can show you how to pick which direction. So this is the x direction. I'm going to draw it in red right here. And so I want the component on this direction, and that component is the 4/5. So for this, for f of x, for sum of x, sum of forces in the x, I'm going to write FC times 4/5. And of course, if this is the positive x, this component is going in the negative x, so it's negative. Okay. Now for FD, that's in the xy, which means I also have a component in the x direction. And I know here, I'm going to erase this now so I can show you what to do with FD. I know that there's a 30-degree angle between the force and the y-axis here. So that now that I want this opposite, I want the opposite, which means I'm going to use sine. So I'm going to say this is plus FD sine 30 equals 0. I have nothing else acting in the x direction. Okay, let's sum in the y direction now, set that equal to 0. So in the y direction, I'm going to have to deal with, of course, this FB force that's purely in the y, and it's in the positive y. So I'm going to start with FB. Now, the other force I have is FD, right, because it acts in the xy plane. And I'm going to have minus FD because it acts in the negative y. And now I'm going to have cosine 30 because that's the adjacent, right? I'm looking for this component of this force FD. So this is the adjacent, right? This was the opposite. So this would be FD sine 30, right? Adjacent and opposite. Okay. And that's all I have in the y direction. Last thing I have, last equation, and I'm going to have two forces in that direction as well. So the FC component, right? I'm going to come here. Let me erase this information so I can show you now. The FC component, this is FC, right? I have the X component in this direction, and I have the Z component in this direction, right? So because it's vertical, I'm going to use the 3/5 now for that. So for Z, I'm going to have FC times 3/5 minus that 90 pounds acting purely in the Z direction. And I can solve now. I have 3 equations and 3 unknowns. So I can solve algebraically for all of these, and I get FC is 150 pounds. I get FD is 240 pounds, and I get FB is 208 pounds. And they're all positive, which means they're all in tension. So all positive means all in tension, which means they're all pulling on point A. All of these points, these cables, they pull on point A. They're all in tension. Okay, now the next thing we want to get is we want the spring force, right? So the spring force here, we have FB is equal to K times SAB. And we have 208, which is the spring force. We're given a K of 500 pounds per foot, and we're looking for that stretch in the spring SAB, and we can directly solve for that here, which is 0.416 feet, and you can leave this in feet or you can convert it to inches, whichever one you like, okay? So pretty straightforward, very similar to 2D systems. We just have one extra direction that we get to solve for our problems in now. Okay, let's do another example here. We also want to determine the force in each cable. Very similar problem, we just kind of don't have to deal with the spring. I'm going to use Cartesian vectors for this problem just because these aren't as straightforward in the given direction. So you can choose either method that you like, but for this problem, just to show you a different way, I'm going to use Cartesian vectors actually. So I'm going to start here by drawing our FBD again. Let me draw the axes first. Okay, so this is my Z, this is my Y, X, Y, Z. And here, my FD force, that cable FD, I'm going to draw that purely on the X axis, the positive X axis. I have FC here, something like this. And I also have FB. And in this case, I'm not necessarily given in the problem which axis or which planes these cables act on, but I'm given all of the coordinates for them. Okay, I'm given all the coordinates. Oh, and I can't forget the 40-pound crate. Let me get that here. 40-pound crate, right? So what I can start by doing here, I'm going to start by defining point B and C by their coordinates. So point B acts at an X value of -3, a Y value of 4, and a Z value of 8. And point C is at an X value of -3 as well, a Y value also of 4, and then an X value, actually wait, point C, X is -3, Y is 8, right? Y should be 8. And then the Z should be 8 as well. There we go. Okay. Now what I can do that I have those coordinates, I can actually write FB as a vector, and I can take the magnitude of FB multiplied by our Cartesian vector system here in terms of our unit vectors. So I need to travel negative 3i minus 4 in the j plus 8 in the k. And then I'm going to divide that by the magnitude of that vector. So I'm using the same concept here that I did for Cartesian vector coordinate systems to define what FB as a vector would be. I'm just multiplying all of this out. FB and the K. And now I'm going to do the same thing for point C. So, or vector C. So I can say vector C is equal to the magnitude multiplied now by here. Actually, here I made a mistake. This is a little bit difficult to see. This coordinate here is actually at -4, and C is actually -3, 4, 8. So let me explain what's happening here. I made a small mistake. So this here is the z-axis, and there's one cable on one side of the z-axis here, and one on the other side. So they're actually showing us 4 and 4, not 8. Yeah, it's a little bit difficult to see, but there's actually a 4 on the negative, which is where B is, and a 4 on a positive where C is. So make sure you guys make that correction, okay? So now I can come back here and multiply it by the unit vector to get that direction in. So 3i, now it's going to be plus 4j plus 8k divided by the magnitude of this, which is -3 squared plus 4 squared plus 8 squared. And I end up getting that FC is equal to -0.318 FC in the I direction plus 0.424 FC in the J direction plus 0.848 FC in the K direction. And now I also have FD, right? I have this force FD here that's purely on the X, and I don't really need to do very much for that because it's not acting in any direction. FD is just acting purely in the I direction, the positive I. And then I also have my W, which is just that -40 in the K. So these are really all of the forces I have acting. I have FB, I have FC, I have FD, and I have W. So this is a little bit of an easier approach to use when we don't exactly know which planes the forces are acting in, when they're acting in multiple planes, right? And the reason for that here is you can see my FB and my FC, they have some component in the I direction, they have some component in J and some component in K. So they're not just acting in two planes anymore. They're acting in multiple planes. That's why it's much easier to separate this with Cartesian vectors instead. Okay, so let's continue now. We're going to set up equilibrium here. And let's sum our forces and set them equal to 0, right? So what that means is we're going to take our FB vector plus our FC vector plus our FD vector plus our W vector, and we're going to set that all equal to 0. So I'm not actually going to write all that out. What I'm going to do is I'm going to separate that into our X portion, our Y portion, and our Z portion. So I'm going to go to FB, and I'm going to take the I from FB, which is the -0.318 FB. Okay, so I'm done with FB for X. FC's X component is another -0.318 FC. FD's component is just plus FD. And then W does not have an X component or I component, and so that's just going to be 0. I'm going to do the same thing in the y. So basically this is summing fx equals 0. This one here, I'm going to sum fy instead equal to 0. So fb component in the y is negative 0.424 fb. fc's component, let me fix that b before I continue, is plus 0.424 fc. FD does not have a y component and W doesn't have a y component, so that's just equal to 0. Okay, so actually I can simplify this. If I move FC over, I end up getting that FB is equal to FC. I'll deal with that later, right? The last thing I'm going to do is the Z component, right? So this is summation of forces in the Z direction equals 0. And for FB, I have 0.848 FB. For FC, I have plus 0.848 FC, and then I have just the negative 40, right? So now I can see that basically if I solve for all of these equations, I get FB equals FC equals 23.6 pounds, and I get FD equals 15 pounds. Now you can always use Cartesian systems if you'd like. Sometimes it's easier if everything is already in a 2D plane or a 2D system, then you kind of don't need to do anything with that. Okay, you can just do it regularly. You can just sum forces in the x and y. You don't have to do any Cartesian vector analysis with that. Okay, so two different approaches towards solving problems in 3D here. Okay, now that pretty much covers all of particle equilibrium. Okay, now it's really important that we get these concepts down because we are going to be moving to equilibrium of systems later. So it's really important that we get particle equilibrium before we add on more complexity to the situation. So in order to really drive that concept home, I have a few more examples that I wanted to share with you guys here. So definitely you could always try these on the PowerPoint slides that I've put up for you first, just to test yourself, and then maybe come and watch these solutions to see if you need some extra help. But that's the best way to really see if you're understanding what's going on through this lecture, is by stopping this video right here, going and trying these examples from the PowerPoint slides that I put up, and then coming back and watching my solution for all of them. Okay, so I hope you guys take that advice, and I hope now you guys are back from pausing the video and trying this on your own, and now we can go over the solutions together, okay? So this is a video, so you can disregard that this is an in-class assignment here. If this were in class, we would have submitted this, and we might still do that. So let's go ahead and talk about 3-29 and 3-30. These are both problems from your book. So what we want to do here first is we're going to focus on first 3-29. So we want to determine the tension developed in each chord required for equilibrium of the 20 kilogram lamp. So we're going to start with that part first. So what I'm going to do is I'm going to start this process by drawing a free body diagram. Of course, that's always going to be the first step to these problems. And I'm going to call this FBD at point D, because as you can see here, we have point D and we have point C. So we can use multiple free body diagrams, multiple equations of equilibriums to solve for multiple unknowns, which is nice. So I'm going to first do my free body diagram at point D. And what I have at point D, I have a 20 kilogram lamp that was stated in the problem. So 20 G, right, because kilograms is a mass. And I have FDE from that cable above, and I have FCD or FDC, whichever one you want to call that. And remember, this is point D. Okay, now I'm going to put this FDE force into components. We have a 30-degree angle that this makes with the horizontal, so I have FDE cosine 30 here. And I have FDE sine 30. So now I can go ahead and sum forces in the x direction, set them equal to 0, and I get FDE cosine 30 minus FDC equals 0. Now I'm going to sum forces in the y direction. Up is positive, and I'm going to say FDE sine 30 minus 20G equals 0. And I can directly actually solve for FDE here. You see I'm going to put the 20G on the other side, and I get FDE. Remember, G here is 9.81 meters per second squared. I end up getting FDE is equal to 392.4 newtons, and I can go ahead and plug that in, and I can solve for FDC, and I get 339.8 newtons. So I'm done with 2. Now to get the rest of them, I'm going to do another FBD now at point C. So I already solved for FDC, which is the same as FCD. So FCD would be equal to the 339.8 here. And then I have 2 more unknowns. I have FCA and I have FCB. And I'm going to draw my axes here to make everything a little bit easier. Okay, now let's put these into components. So I know that this is a 45-degree angle right here, so I can put FCB easily into FCB sine 45, FCB cos 45. And then for FCA, I'm given that it's a 3, 4, 5 triangle, so I'll put those into components when I sum the forces in each direction. So to sum the forces in the x direction, I end up getting the 339.8 minus FCA times the 3/5 component minus FCB cosine 45 is 0. Okay, and I can, I'm going to leave this actually like this for now. I can't really do very much because I have 2 unknowns. So before I simplify that further, I'm going to come here, let sum forces in the y direction. Up is positive, and I get FCA times the 4/5 component minus FCB sine 45, set that equal to 0. And what I can do is I can simplify this and say that FCA is equal to 0.8839 FCB. And now I can take this is just 2 equations and 2 unknowns, plug it into there. And what I would get is 339.8 minus 0.8839 FCB times 3/5 minus FCB cos 45. And I can solve now just for this one unknown here, FCB, as 274.6 newtons. And now that I have that, I can plug it back in for FCA, and I get 242.7 newtons. And now I've solved all of the unknown forces for problem 3-29. Okay, so that is the procedure for that first part of the problem. Okay, now what we're going to do is we're going to do 3-30. So let's go back up and read 3-30. So we want to determine the maximum mass of the lamp that the cord system can support so that no single cord develops a tension exceeding 400. Okay, so what we want here, we want the max tension in any cord to be less than or equal to 400 newtons. Okay, so what we want to do is this. Let's look at the 4 numbers we got. For FCA and FCB, we got 242, 274, FCD and FDE, 392, and 339. So FDE here is actually the cord with the highest tension. So what we're going to do is, because that's the cord with the highest tension, we're going to set FDE equal to 400 now. And we'll say, well, that's the max it can go. So if FDE is 400, well, this is point D. Let me draw my FBD now if that were 400. So if FDE were to be equal to 400, And I would still have now FDF, and I'd have FCD, right? What would these other tensions be? What would happen here? So I could sum forces in the x direction, right? And remember, FDF here at point D, this actually is the weight. This is equal to the weight. Right? We want the mass, but we can get the weight at least by this, right? Then we can plug it in and solve for the mass. So I'm going to say this direction is positive. I would have 400. This still makes the 30-degree angle minus FCD equals 0. And I can solve for FCD as 346.41 newtons. And I'm going to sum the forces in the y direction so I can solve for that weight. I get negative FDF plus 400 sine 30 equals 0, and I get FDF equals 200 newtons. And basically this is the max weight. This is the max weight. I want the max mass though. So all I have to do is say W over G is equal to M. So if I divide this by 9.81 meters per second squared, I end up getting 20.4 kilograms. And that's the maximum mass that we can have in the lamp so that no cord experiences greater than 400 newtons of tension in it. Okay? All right, so next extra problem we have here, example 7. This is the last problem we'll do. So we did one 2D problem, one extra 3D problem here. So now what we want to do, we want to look at the system, and they're telling us that the max force in each rod can't exceed 1,500 newtons, so we want to know the greatest mass of the crate. So this is the same problem as we did before. The only difference here is that, one, we haven't already done an analysis to see what our max force would be, which one of these would have the max force. And the second thing is this is now a 3D system. Okay, so those are the big differences here. So the first thing we're going to do is let's draw our FBD. So we have X, Y, and Z. Here we're going to have some force FC. We're going to have some force here FB. This, I'm just going to draw my negative Y. Somehow my Y got removed here. There we go. And then we have also our W, which is equal to mass times gravity, right? Okay, so again, I'm going to use Cartesian vectors here just because I'm not sure which planes these are acting on. They're acting on multiple planes, okay? So I'm going to set this up by first defining point A. We have to go 2 for point A, then 3 over in the Y, and then 1. For point B, we're going to have to go 1 in the X, 2 in the Y, 2 in the Z. And point C, we're going to go 3, 2, 3. Hopefully I did these ones right this time. Okay, the position vector, the magnitude of that is going to be root 14 for A. Magnitude of the position vector at B is 3. Magnitude of the position vector at C is 22. And remember, the way I got these, I'll show you one of them. It's just taking the square root of A squared plus the ax squared plus AY squared plus AZ squared. So you just do that for each one, and you're able to get the magnitude. This is the same thing as me writing the way that I did this previously for this example here. Let me find it for you. For this example, this is the same thing as me writing it like this. I'm just kind of cutting out this extra lengthy step and getting right to it basically. Okay. Okay, so now I'm going to cut right to the chase and start summing forces in the X direction. So for the A, I would have whatever the magnitude of A is times the X component, the 2 divided by that magnitude, minus my FC component times 3, because that's my FC here, the 3, divided by root 22, plus FB times 1 over 3, and that equals 0. So this is a little bit of a quicker way. Once you've been solving a lot of problems and you get the hang of it, you can equals 0 equals 0. You can start setting these up a little bit quicker this way. And then our last equation, sum of fz equals 0. We have fa times 1 over root 14 plus fb times 2 over 3 plus fc times 3 over root 22. And then don't forget minus w. Okay. So now what I'm going to do, actually, I'm going to change this w and put in mass. I'm going to write this in red so we all know what's happening. I'm going to write this as mg, right? Because w is equal to mg. And what I'm going to do is I'm going to solve for each one of these in terms of m now. So if I do that, I can solve for fc as 16.95 in terms of m. I can solve for fa as 15.46 in terms of m, and I can solve for fb as negative 7.745 in terms of m. Now, the link OC here, let's come back to this. Our link OC is the largest force. This has to be our limiting force, right? OC, because we see that that's going to be 16.95 times m. So our largest force here is going to be this one, right? So we know this has to be our limiting force. So we're going to set this equal to 1500 newtons. And if we do that, we get 1500 equals 16.95 m. And then we would solve for m as 88.5. And sure enough, if we were to plug this in to any of the FB or FA, we would not get over 1500 because it's less than 16.95 for both of those. Okay? And that's it. Okay? So you guys can continue practicing these problems from your suggested problem set. And then this is the last video for topic 3.